I have a huge jar of pennies at home, always saving for a rainy day. It can hold thousands of pennies. It would be tedious for me to count each one of these one by one, which is why banks have machines that do this for me. But I don't have a coin counter at home. Instead, I can estimate the number of pennies by using a balance to determine the total mass of the pennies. If each penny weighs 2 grams, and my jar contains 2,000 grams, I must have 1,000 pennies. This is real chem. When counting particles, such as atoms or molecules in chemistry, there are two concepts to get familiar with. One is using mass as a way to count particles. The other is using the mole as a unit for reporting those counts. Let's explore. In chemistry, we often want to know the number of particles in a sample, such as a jar of water. This has a lot in common with counting the number of pennies in a jar, but there are some important differences that arise from the large differences in scale. A jar of water contains many sextillion water molecules. It would be incredibly difficult to count this many of water molecules one by one, even with a fancy machine. We get around this challenge by using a trick similar to the shortcut I used to count pennies. We determine the mass of the water in the jar and then use the mass of a water molecule to figure out how many water molecules we have. I can get the mass of a water molecule from the atomic masses on the periodic table. Hydrogen has an atomic mass of 1.008. Oxygen has an atomic mass of 15.999. A water molecule has 2 hydrogens and 1 oxygen, so the mass of a water molecule is 18.015. But what are the units of this number? There are 2 common answers to that. The first is that the units are atomic mass units, or AMUs, giving us 18 AMUs per water molecule. We could look up the conversion from AMU to grams to determine the mass in a unit we're more familiar with, but a more convenient approach is to view the units of the molar mass as being grams per mole, or 18 grams per mole for water. A mole of water molecules is Avogadro's number, or 6.02 times 10 to the 23rd water molecules. If the water in our jar has a mass of 100 grams, it has 100 grams times 1 mole over 18 grams, or 5.55 moles of water molecules. Does this correspond to a count of water molecules, or should we use Avogadro's number to convert literally to the number of water molecules? Let me use an analogy. If you asked me for the number of eggs in the produce aisle of a grocery store, and I responded with 55 dozen, would you accept the answer? It is a count of eggs, it's just using a dozen as the unit for the answer. In chemistry, when asked how many molecules are in a sample, we usually reply with the answer in moles. 5.55 moles is just way more convenient than saying 3.34 times 10 to the 24th molecules. It's still a count of molecules. Using mass to count particles is one of the oldest tricks in the chemistry book, and one of the oldest ways to count coins. We often need to know how many molecules are in a sample, but this doesn't mean we have to count them one by one. Instead, we can just determine the mass of the sample and use the molar mass to figure out how many molecules we have. So, explore, and remember to have fun.